All right, welcome back to the number theory and encryption slides. Today we are finally going to get to encryption, so I'm excited for that. We do have a few pit stops along the way, but let's get started with number representation. So this is something I think you're required to learn about in CSCI 40, but let's just like revisit it all over again with our new knowledge. So we can write things in different number systems. Different bases exist, right? You got binary, you got base 10. So the number system that we know and love as humans is decimal, and it's also called base 10, right? Because it has 10 digits total. So when you're making a number in just the normal number system that we use every day, the valid digits that you get to use, right? Valid digits that exist in base 10. Valid base 10 digits are 0 through 9, and there's 10 of them. Those are all the digits that you get to use to make up all the numbers that you know, and that's how we write our numbers, with some combination of these digits. And the reason we think we think in base 10 is because we have 10 fingers, and so maybe if you lived in the Simpsons world, you'd be thinking in base 8, where you only have 8 valid digits to use. And so we're going to be talking about different bases, and I hope you've seen this notation before, but just to make it clear, like this is the number 42. If I write a subscript 10 here, I mean decimal, all right? I'm talking about the 42 that you know and love, all right? So this means 42 in decimal. If I put a little subscript like that, that's saying this number, consider it in this particular base, because there's more than just base 10, okay? Let's see. And yeah, so if, for example, if I use base 5, if I was working in base 5, which digits could I use? How many do I get? You get 5 digits total, and it's going to be 0 through 4, right? 0, 1, 2, 3, 4, and you can build up numbers with these and consider it to be in base 5. Like 4 and 2 exist still in base 5, but 4, 2 in base 5 is not equal to the number 42 in decimal. Does that make sense? So this would be equal to 102, I think. Don't quote me on that. Or no, maybe 20. Sorry, no, 20. This would be 22, I think. We can check that later. But yeah, so the way that you can convert, by the way, if I ever gave you a number that was in a weird base like base 5, you can always convert it back to decimal, because that's the number system you know and love, by using the expansion, the power expansion of a number. And so let me give you that. Let's do that in decimal first, because this idea that I'm about to show you generalizes to arbitrary bases, okay? So for example, remember how you broke down this number 1,234 in like elementary school? Somebody told you like, oh yeah, 1,234, that's equal to 1 times 1,000 plus 2 times 100, the hundreds place, right? Plus 3 times the tens place, plus 4 times the ones place. So trust me, I'm going somewhere with this. And then when you learned about exponents, you learned a different way to write this. This is like 1 times 10 cubed plus 2 times 10 squared plus 3 times 10 to the first plus 4 times, you can still get a 10 times 10 here, but you have to put it to the 0th power. And notice, when you're breaking down this decimal number, base 10 number, do you see where the base appears? It appears in these exponents here. So that is going to be the trick, and that's going to be the secret to breaking down any number written in any base. All right, it's just going to be like times 5 cubed times 5 squared if you're going to break down a base 5 number. So yeah, the base b expansion for some arbitrary base b is exactly what you would expect. So let's take 1, 2, 3, 4, because it's not 1,234. Let's take 1, 2, 3, 4, that number in base 5. Let's convert it to decimal. All right, so 1, 2, 3, 4. Base 5, that's equal to, well, you usually start at the right. You're like, all right, this is the 4's place, 4 times, that contributes 4 times 5 to the 0, right? You always start times the base to the 0. And then this is 3 times 5 to the first, plus 3 times 5 to the first. And then this is 2 times 5 squared. It's like the 25's place. And then this is 1 times 5 cubed. It's like the 125's place. So if you break this down, that's 125 plus 50 plus 15 plus 4. If you do the math, apparently the answer is 194 in decimal. Right? So that is how you would solve for that. And it's always going to be, you use the base that you got. You're breaking it down into powers of that base. And that's how you do math and eventually come up with whatever it was supposed to be in decimal. All right. So that's the idea. And this way of breaking down numbers, this style of doing things, this works when you go from an arbitrary base to decimal. Okay, that's the idea. And so you just look for that, and that will give you the answer there. So that is number representation, and we of course love binary in computer science. That's base 2, right? So base 2 is binary. What are the valid digits that you get? Of course, you have 2 of them, starting at 0. So you get 0 and 1 to build all of the numbers ever. Okay, and instead of saying binary digit all the time, everybody was like, oh, let's shorten that. Take a B from the word binary and IT from the word digit, and we'll call it a bit. So every digit in a binary number, we say bit for short. So this, for example, is a 5-bit number. It's got 5 binary digits, and it's a base 2 number. All right, so let's convert it to decimal using the same idea that we were talking about before on this slide. So this is going to be the 2 times 2 to the zeros place, right? 1 times 2 to the 0 plus 1 times 2 to the first plus 0 times 2 squared plus 0 times 2 cubed plus 1 times 2 to the fourth. Yeah. And so what was that number in decimal? Well, it was 16 plus 2 plus 1. So that's 19 in decimal land. And so that's how you would convert it. Okay? So that's decimal in a nutshell. We love base 2. 8 bits, by the way, that makes up a byte. That's a unit of space. So like the smallest byte number is 8, 6, 7, 8 bits total. So it's just 8 zeros. And the largest byte would be 8 ones. And I encourage you to calculate, well, that's going to be the number 0. What number is that if you don't remember it? Okay? So we also like, in addition to just base 2, we also like bases that are just powers of 2. We work a lot with hexadecimal in computer science and a decent amount with octal, so I'll teach you that too. So octal is base 8, all right? So it's 2 cubed. And so there's going to be a correspondence between binary and octal, and also binary and hexadecimal. But octal is base 8. That means you get how many digits to work with? You get 0, 1, 2, all the way to 7, 8 digits total. Okay? And one thing that octal numbers are good for is permissions inside of a file system. So in Linux land, if you do ls-l, it shows you a bunch of files, and it shows you their permissions. You have the ability to, like, for every file, like, can you read, write, or execute it if you're the owner? Can you read, write, or execute it if you're the group that the file belongs to? Can you read, write, or execute it if you're just anybody else who is looking in on this file system? And so you have 3 options, right? You have 3 bits for the owner's permissions, 3 bits for the group's permissions, and then 3 bits for the for everyone else's permissions. And those numbers, those add up to 8, right? You have 8 options for reading, writing, and executing something as a user. So that it makes sense to be able to change these permissions using octal numbers. And I highly encourage you to look into that. There's a chmod command that changes the file mode bits, all right? Maybe it's chmod is how you should say it, but chmod is how I'll say it. But you can give an octal digit, like 755, for example. That's an octal number that corresponds to who you want to have accessing this file /folder. So that's pretty cool. So that's where octal exists. That's the best example I have of it right now, at least. And hexadecimal is probably the second most popular one after binary. So binary and hexadecimal, they go hand in hand. It's very easy to convert between the two. And so I'll show you that in just a second. But hexadecimal is base 16, and so you need 16 digits before you need a new place. That's more than decimal, right? So we need to start adding more after 9, more single-digit things to get 16 digits total. So 0, 1 through 9, and then we start using letters. All right, so A represents a single digit, meaning the number 10. All right, B represents a single digit, meaning the number 11. Same, C is 12, D is 13, E is 14, and F is 15. All right, so that looks a little weird, and so now you can make numbers, if you've never seen this before, with letters involved. All right, let's convert FE in base 16 in hexadecimal, hex for short, to decimal. And so these names come from like the either the Greek or the Latin roots of these numbers, right? Like oct means 8, and then hexadecimal is like deci for 10, and then hexa for 16, or for 6, and so that makes 16. That's how you can remember it. So FE, let's convert that to decimal. So that's going to be, well, it's going to be E, right? E times 16 to the 0 plus F times 16 to the 1. Okay, and so you can check this. What is E, first of all? E is 14. That's going to be 14 times 1. And then this is 15 times 16. 15 times 16 plus 14 times 1, or 16 to the 1, whatever you want to think about. So that's how you can convert it. And then apparently, if you do the math, we have 15 times 16 plus 14, that's 254. That's what that meant in decimal land, all right? If you want to type, sometimes it's easier to write hexadecimal numbers rather than binary numbers inside of a computer program, and so you can't really type a subscript as part of like a C++ program or a Python program, and so people have came up with the shorthand starting with 0x, the prefix 0x, and then if you write your number, it means to your programming language, like this number, interpret it as a hexadecimal number rather than a normal decimal number. Okay, so if I say 0xFE, Python will translate that immediately to 254, because that's just how that works. That just prefixes a hexadecimal thing. Same with 0B for like binary. That's a thing. 1111, that's 15. And I think 0O also exists. 0O, 755. So that's how you can type an octal number. Those are just little prefixes that mean, like, don't treat this as 1111. Treat it as a binary number, right? Because that, you can run into trouble when you do hexadecimal, right? 100, you think that's the number 100, but no, in hexadecimal, it's the number 256. So we use those prefixes a lot of the time to do cool stuff. Oops, sorry. Knocking things over on my desk, but that's different bases that are powers of 2, and it's very easy to convert between those bases. But let me show you just the arbitrary way of going backwards. All right, so I taught you how to convert from some weird base to decimal. I need to teach you the other direction. I give you a decimal number, you go back to whatever the number is in some weird base, okay? And so, again, there's going to be an idea that looks very similar to what we learned in like elementary school. Like this was how you split up a number based on its powers based on its digits in each place, and that generalized to any base. We're going to do the same thing in the opposite order. So let's come up with an algorithm to extract the digits of the number 1,234. Okay, and so the secret is going to be you're going to work your way from the right inwards. So you're going to try to extract the 4, and then cross off the 4 to make 123, and just keep hitting the rightmost digit of every number. So let's figure out how to do that with just decimal numbers. Let's extract the decimal digits of a decimal number. Have you seen this before? How would you extract the last digit using math of 1,234, just the normal decimal number, 1,234? How would you get the 4 out? All right, with some generalizable mathematical thing. What would you do to 1,234? Well, if you think about it long enough, if you do mod 10 on this number, well, it goes in 123 times with 4 left over. So that's how you get the 4, all right? And so now you know how to get the rightmost digit of any number. If only I can just like get rid of that 4. Like here's the idea, like 1,234, we figured out like the process to get the 4. What do? It was mod 10. And then now if only I could do the same 1,234, turn it into 123 with some operation, because then that kind of like chops off the 4, and then I can get the rightmost digit of that, and I can keep on redoing this process. Okay, so how do you get all but the last digit of 1,234? How do you turn it into 123? It's kind of the opposite, right? I said it. You divide by 10, and you skip over the remainder. No decimals or anything. It's integer division, right? Our good old integer division from like C++. This is integer division by 10. That turns 1,234 into 123. And then you can just keep doing that process to extract digits, okay, of a number. So let me show you how to do that. Let's extract all the digits from 1,234, assuming it's like a black box and we can't really look at it, but we can do math on it, okay? So how do you get the rightmost digit? It's going to be mod 10 first, and that will give you back the 4, the rightmost digit, yeah? And now if only I can chop off the 4, then I can do the same thing, get the rightmost digit of 123. So how do you turn this number? How do you shift away the 4 or chop it off? You do integer division by 10. And so that turns it into 123. And now you work with this number. Now you extract all of its digits, all right? And so this is extracting decimal digits, but this idea generalizes. Do you see where the base appears? So mod 10 on this gives you the 3 because it goes in 12 times with 3 left over. And now let's shift away the 3 in decimal land. Let's do integer division by 10, and that will give us 12 now. Let's extract all the digits of 12. What is its rightmost digit? Again, we can do mod 10 all day long, okay? That's the idea, okay? Can do that. Sorry, let me write a better 10. Okay, so it goes in once with 2 left over. All right, let's chop off the 2 now. Let's convert it into a smaller number that I can extract the digits of by doing integer division. That goes in once, right? Chopping off the remainder, any decimal places, just normal integer division. And now let's extract all the digits, the decimal digits of the number 1, because why not? 1 mod 10, it goes in 0 times with 1 left over. And all right, let's shift away the 1 from this number, see if there's anything left to do. 1 integer divided by 10. We hit 0, and that's how you know when the process is done. That's the algorithm, all right? And so every time you took a modulus, you did the modulus operation, you got a digit of your number in reverse order. So this was 1, 2, 3, 4, and those were all the digits. Does that make sense? That's the secret, and that's how you extract the decimal digits of a decimal number. And if you wanted to convert, do you see where the base appears, right? If you wanted to convert a decimal number to instead maybe binary or some other base 5, base 7, then you could do modulus and integer division by the base you're trying to convert to. Okay, that's the secret. That's how it generalizes. Okay, so that's how this works. Let's convert 55 in decimal to base 7. Let's figure out what that answer is. And you can always check yourself because it's easier to do the other way. Right? So let's convert 55 decimal to base 7. What is it going to be in base 7? So you start with your original number, and we want to extract the rightmost, not decimal digit now, but the rightmost base 7 digit from this number. So I'm going to do mod 7, because that's the base I'm trying to get to. 55 mod 7, no, I think it goes in 7 times to make 49 with 6 left over. We can confirm that. Hey, there we go, 6. So there's that. So 6 is going to be the rightmost digit of this number 55 in base 7. But we need the rest. So let's chop off the 6, right, in the base 7 representation of 55 by doing 55 integer divided by 7. That's 2 slashes in Python. So that gives you 7 back. And so now we need to convert 7 to base 7, and then we'll be done. Tack a 6 at the end of it, all right? So, all right, what's the rightmost base 7 digit of the number 7? Well, it goes in 1 time with 0 left over, so that was a 0. And let's chop off that 0 from the base 7 representation of the number by doing integer division by 7. So that gives me 1, and now this is a new number to convert to base 7. 1 mod 7, what's the rightmost digit in base 7 of the number 1? Well, it goes in 0 times with 1 left over. And then let's see if there's anything left to convert by integer dividing by 7, chopping off that 1 from this number. In base 7, of course. So that gives me 0, and that's how I know I'm done. Okay? So that is the process, and then every time I took a modulus, this time it's by the base I'm trying to convert to, right? Well, I guess it always is. Every time I took a modulus, I got a digit of this number in reverse order. All right, so I got a 1. The number, the answer is 106. Okay? 106 in base 7. That is the number 55. Does that make sense? And you can always check yourself, because this is 7, this is 6 times 7 to the 0, right? So that's just 6 times 1, plus 0 times 7 to the first power, plus 1 times 7 squared. That's like the 49's place. That's 55. All right, so you can always go the other way. That's the easier way. And that is how you can convert between arbitrary bases, all right? So if you want to convert, for example, like if I gave you a question of converting from, I don't know, what is 55 in base 8, how would you convert that to like base 7? Something base 7, right? Instead of making this entire jump, what you can do now, I've given you the tools, you can go straight, you can convert to base 10 first. You can get this number like, what is it really in decimal? That's something in base 10. That's the easier direction, right? And then you have a decimal number. You did it this way, right? Figure out what it is in decimal, because then this algorithm that I just showed you takes a decimal number to any base, all right? And that's the two-step process you can always go back to if you need to. All right? You can always start with the number in decimal, and that's how you can go between arbitrary bases if you go and make a pit stop in decimal land. All right? There are some shortcuts though if your bases are powers of each other. Okay, so powers of 2, of course, is what we care about. So there's some cute tricks to convert between binary, octal, and hex very quickly. All right, so let me show you those tricks. So, all right. First of all, do you see in this picture that these are every digit, right? These are hexadecimal digits all the way to F, which is 15. Do you see how they correspond exactly to every possible 4-bit number, going from 0000 all the way to 1111? So there is a very clear correspondence between 4-bit numbers and hexadecimal digits. All right, that's going to be the secret. All right, that's how you can go between them very quickly. All right, so I'll give you an example of going between binary and hex, but it also works between binary and any other power of 2 base, like binary and octal, for example. Okay. So here is the secret. Dun, dun, dun. If you add a 0 in binary, I'll try and prove to you why every hex digit corresponds to 4 bits. First of all, if you add 0 to the end of a number in binary, you're multiplying it by 2, right? Because 1, 0, just like in, for example, when you're multiplying by the base in decimal land, you multiply 10 by 10. That adds a 0, right? 10 by 10 by the base takes that original number 10. Or maybe I should do something different. Let's do, I don't know, 23. If you multiply that by 10 in decimal land, right? This is decimal numbers I'm talking about right now. If you take it and you multiply it by the base, that adds a 0, right? That makes 230, right? It takes the original number and tacks a 0 at the end of it. So similarly, and it's like adding a 0 in decimal multiplied by 10. Adding a 0 likewise in binary multiplies by 2. Okay, so that's important. And then also adding a 0 in hex, what does that do? It multiplies by 16, doesn't it? What does that mean in binary, right? If you add a 0 to a number in hexadecimal, like I had F, and I added F0, now it's F times 16 plus 0. I just multiplied by 16 by adding a 0 at the end of a hex number. So how do you multiply by 16 in binary? You add 4 zeros. You multiply by 2 4 times, because 2 to the 4th power is 16, all right? So I hope that's making a little bit of sense. And so every hexadecimal digit corresponds to 4 bits at most, okay? Because 1111 is the biggest hex digit, that is F, okay? So the secret's gonna be just read off the digits. Just read off the digits, and that's how you convert. Always making sure to like pad with some zeros if you have 3 in hex. Just read off the digits. That's going to be the secret. Let me prove that to you. Let's convert DE in base 16 to binary, not using the long way. All right. Remember that DE in hex is the same as, well, the D in the 16's place plus the E. So D0 plus E. It's the same number. Yeah, just broken down. What's that equal to? That's equal to D times 16, right? Because adding a 0 to the end of something multiplies by 16. Adding a 0 in the base multiplies by the base, plus whatever E was, okay? And what's that equal to? What's D times 16? Well, D is this number, right? D is the number 13, right? D is the number 13 in binary. What is that? Because we're trying to convert this to binary, right? D in binary by itself is this. That's your 13, 1101. But we're multiplying it by 16, which means multiply it by 2 4 times, so add 4. And do you see, that's binary now, so that's D0 in binary. Do you see how we just left 4 digits room for the other one? So every hex digit is going to correspond exactly to 4 bits. So then we're going to add in the E, which is the number 14, which is 1110 in binary. And you see how we don't have to carry or anything? It just goes right here because we left room. It's perfect. And so you just read it off. That one plus that one. They both go in the right way. That's equal to, you just read it off the table. DE in binary, oh yeah, that is going to be 1101, 1110. Read off the D, that is 1101. And then read off the E, that is 1110, as long as you give 4 bits for everything. That's going to work out, okay? So that is the answer, and that's why you can just read it off, okay? That is the secret. That's how it works. I hope that made a little bit of sense. Because of all these key ideas coming together, you can just read off a table, just like convert every hexadecimal digit to 4 bits, and you're good to go, okay? And you can go in the opposite direction. You can convert this binary number to hex very easily by circling groups of 4 bits. Like here's a group of 4 bits. You start at the right, of course. Here's a group of 4 bits, and then here's a group of 3 bits, but you can imagine like there was a 0 right here. Not a big difference, right? So what's this? You can really read it off, right? The answer is going to be, well, this is 7, right? 7, this is 4, and then this one is A. So the answer is going to be 7, 4A, all right, in hexadecimal. And I'll prove that to you, all right? Because we can do this math as well. Because what is this but 0, 1, 1, 1 with a bunch of zeros at the end, 4 zeros. So this is in hexadecimal land. This is 7 with room for 4 or 8 sets of zeros. So 2 hex digits, 2 groups of 4 bits. So that's 700 plus, what is this one? That's equal to 40. These are all hexadecimal numbers. Just read it off, and it really will work. And then this is going to be our digit A in base 16. Okay? And the reason it works is because, like all of these things, these are all powers of 16, right? Groups of 4 bits are powers of 16. All right? So that's how you can read it off. So every 4 bits is a hexadecimal digit, because 2 to the 4 is equal to 16. All right? That's going to be your secret. That's how you can go very quickly between powers of 2 bases. So yeah, I think you can imagine that it's very easy to convert to octal as well, between octal and binary. And if you go through binary, you can go from octal straight to hex if you wanted to. So that's a lot of ideas. I've given you a ton of ideas. Let's talk about them. All right, so here's what I want you to do. Convert this number, this decimal number 55 in decimal, starting there, convert it to binary, hexadecimal, and octal, and then convert it to base 5 as well. All right, so you've got some options. These 3 kind of go together because they're all powers of 2 bases. You might get off easily. Think of like the best first one to go to. But then you also have base 5. All right, so let me like flip between these ideas, all these slides that you might want to look at. So I've given you a bunch of ways to get there. Try to do this, and I'll show you the fastest way I can think of. All right, so I think the fastest way, honestly, is to convert to hex, and then go from hex to binary, and then from binary to octal. But even if you didn't know that, let's start with binary. Let's just go straight to binary. That might be the easiest one, just to show you all my ideas, because then you can go from binary to hex and binary to octal as well. So let's go from 55 to binary. So let's get the rightmost bit of 55, 55 mod 2. Well, it's an odd number, so there's 1 left over. So the rightmost bit of 55 in binary is 1. And then let's shift away that 1, 55 integer divided by 2. That's going to give us what? Oops. Oh, sorry, I'm not in Python anymore. 55, 21, or sorry, just 2. 27. All right, let's convert 27 to binary now. So 27, what's its rightmost bit? 27 mod 2 is again 1 because it's odd. And let's shift away that 1 in binary land by integer dividing by 2. And so 13? I think the answer is 13, yeah, because it goes into 26 with 1 left over. And then, all right, let's convert 13 to binary. 13 mod 2. Odd again, so we get a 1. Lots of 1s in this number. All right, let's shift away that 1 by doing 13 integer divided by 2. and so that's not 7 but 6, right? 6 with 1 left over. And let's convert 6 now to binary. So 6 mod 2 is going to be, it's even, so the answer is 0. There's 0 left over when you divide because it goes in cleanly. And let's shift away that 0 by doing integer division by 2, getting 3. And now we convert 3 to binary. It's a longer process with binary, but that's okay. It's going to give us the right answer. So the rightmost digit of 3 in binary is a 1 because it's odd. Let's shift away that 1 by doing 3 integer divided by 2, also 1. All right, let's extract the rightmost bit of 1 in binary. Goes in 0 times with 1 left over. 1 integer divided by 2 is 0, and that is the process. So okay, every time, it's a lot, every time we took a modulus, we got a digit in the base we wanted in reverse order. So the answer is going to be 1, 1, 0, 1, 1, 1. That's a long number. That's 55. So 1, 1, 0, remember the order, it's in reverse. And then 1, 1, 1, base 2. So that is binary. And we can quickly convert this to hex, can't we? Just read it off. What's this one? This is, that's a 7. So just write a 7. And then this is secretly 2 zeros, right? 0, 0, 1, 1, that's a 3. So it's 3, 7. 3, 7 in hex, and you can confirm that. It's 16 times 3 plus 7. That really is going to give you 55. And then we can also go quickly to octal, base 8, by just circling groups of 3 this time, because every group of 3 is the numbers 0 through 7, right? The octal digits. So this is the number 7. So there's the number 7. The rightmost octal digit is 7 there. And then 110, that's just 6. So it's really 6, 7. You just read it off like that. That is the octal version of 55. And then base 5 has nothing to do with any of these. So we're going to have to do the algorithm all over again, sadly. So, okay, let's do that one. 55, we start here, and we want base 5. So mod 5, it goes in 11 times with 0 left over. So the rightmost digit in base 5 of 55 is 0. And let's shift that 0 away by doing integer division by 5. So that gives me 11. And let's convert now 11 to base 5. So 11 mod 5. 1 left over, right? Goes in twice to make 10 with 1 left over. Let's shift away that 1. So we got 2. Let's convert 2 to base 5, 2 mod 5. What's the rightmost digit of it? Well, it's just going to be 2. And then let's shift away that 2 by doing integer division by 5. So that's going to give us 0. And so that's the end of the process. Much quicker when the bases are bigger, right? So, okay. Every time we took a modulus, we get a digit in reverse order. So the answer is 2, 1, 0 to get 55 in base 5. 2, 1, 0, base 5. And you can always confirm these, right? This is 0 times 1, plus 1 times 5, plus 2 times 25. Right, so that's 50 plus 5. Checks out. So hopefully this is making a little bit of sense. And hopefully you've seen this before too. We're just building on top of our knowledge. So with that, we've talked about numbers and different bases. We've talked about a lot of cool stuff on previous slides, of course. Don't forget about all that, multiplicative inverses, etc., etc. If my PowerPoint ever wants to load. Let's use all this now. Let's use all this now for cryptography. I'm so excited. Okay, so let me teach you a little cryptography before we go. So here's the setup when you're working in cryptography. You've got something that you want to send to somebody. There's always this metaphor of like there's a sender who wants to send something to a receiver, and the something is called a message. And usually there's like a fun thing to say about it. Like there's like people make up stories. We'll get to that. But yeah, the goal is that the sender only wants the receiver to be able to read the message. All right, nobody else who could possibly listen in or like secretly look under a microscope into the message. Even whatever they do, they still can't figure it out. That's the point of cryptography. They're not supposed to be able to figure out the message at all. Only the receiver, only the person the message is intended for, should be able to decode that message, to decrypt it. Okay, so encryption is a cryptographical idea. It's the process of taking a message and garbling it up so that only the receiver or the parties who you want to have look at this thing can understand it. All right. So there's a lot of terms in cryptography. The unencrypted message, the original message that you're trying to encrypt and send to somebody in a secret way, is called the plain text. You don't want to send that across the internet because anybody can look at a plain text. And the encrypted form of the message, the thing that you do want to send, is called the ciphertext. It's the garbled thing. Okay? So here's kind of like the setup. You're writing a letter to somebody. You're the sender. And here's your plain text. And you're going to encrypt that. All right? You're going to send it through encryption, some encryption processed. You encrypt it, and there's some process that spits out the ciphertext. So that's like the garbled form of your message. All right? Nobody can understand it, except for the receiver. All right? And then the receiver is able to decrypt it. The receiver is going to have some sort of secret key thing that allows them to decrypt the ciphertext and get back the original plain text, so they can read it at their leisure. So this goes through a decryption process. Decrypt. And there's a secret way to decrypt it. Usually we use the word key to mean that. There's a decryption process, and there's like a secret key associated with it. Like here's the key that unlocks the message, and out from that, in a safe place, comes out the plain text all over again. All right, so this is what's being transmitted across the internet pipes, and then nobody else can read it except for the person who's trying to get it. All right, secret key is really a term that's used in cryptography. It's not just a weird, silly word. Okay, so yeah, that's the setup for most of cryptography. And usually, like, people say, instead of like person A is the sender, person B is the receiver in cryptography, in like Wikipedia and like in all the textbooks, they make it cute. Instead of person A, they usually say like Alice is trying to send something, and like instead of B, they just make a name with person B. Like then Bob is the receiver. If you need a third person, then it's like Charlie or something. So it's really cute the way that they write these things. They have some customs in the cryptography world, and I get to teach you about those too, I guess. So, okay, that's cryptography in a nutshell. There's plenty of ways to encrypt stuff. So let me show you a few, and then one cool one that I want you to remember called RSA. All right, so before we get there, let's talk about symmetric key cryptography. All right. In that one, symmetric means like you have the same thing. So in symmetric key cryptography, the sender and the receiver, they use the same key to encrypt and decrypt the message. All right? And so how do they end up with the same key? They need to somehow, like, just think of it like these two people, they need to get together in a secret place, like ahead of time, or communicate through some channel that's already secure. They need to agree on this key together. Okay, in symmetric key cryptography. So that's kind of difficult, all right, because you never know who's listening. So maybe we could do better than this. We'll talk about that. But symmetric key cryptography is a thing. You have your message and you have what you want to send. So as an example of symmetric key cryptography, let me give you some ideas. So for example, our message, let's pretend that our message, the thing that we're trying to send, is a large binary number, first of all. So our message, assume it's in binary, assume it's a number, because binary can, of course, encode anything. Everything inside of a computer is ones and zeros. So you got your message. That's the thing you're trying to send to somebody. All right. One type of symmetric key cryptography is a one-time pad. All right. That's the secret. A one-time pad, it's some random message, some garbled things, like you flip a die enough times and the die has a bunch of letters on it, for example, and it's a way to garble your message. A one-time pad is a random message the same length as the message that you want to send. So it's just a bunch of garbled ones and zeros if you're encoding some binary thing. So your one-time pad is some random number, some very large random number of the same size as your message, all right? And that's called your one-time pad. Okay, it's going to be the same length as your message. If you can agree on this ahead of time, then this will allow you to encrypt stuff, all right? This actually, if you can do this, if you can get away with like giving a one-time pad, if you can make up this random thing and have both parties have it somehow, like before they go off across the internet or something, like agree on it in person, this is a secret key that is absolutely uncrackable. if this is a random message, okay? So that's the idea. So one way to use a one-time pad to encrypt an original message is to use the exclusive OR cipher, XOR cipher. What you do is, because this is a binary number, this is a binary number of the same length, if you just exclusive OR the plain text with your random one-time pad, that can be your ciphertext, all right? And exclusive OR is really nice because it is its own inverse. So if you just do exclusive OR by the one-time pad again, because like the sender has the one-time pad and the receiver also has it, you're going to get back the plain text, which is cute. Okay, so here's the secret. This is symmetric key cryptography. If you get together, you come up with a random one-time pad, a random binary number the same size as your message, you can exclusive OR it with the message. That can be your ciphertext. And then the person on the other end, which also has the same one-time pad, they can do the XOR one more time, and that'll get you the plain text back, which is really cool. All right, so here, let's make it all come together with an example. So let's encrypt and decrypt this message using this one-time pad. All right, so let's say this is our message, 101. We're trying to send this secret message to somebody. Of course, it would be bigger in real life. If you just exclusive OR this with your one-time pad, like this was your random number that you came up with, like you flipped a coin enough times and it landed heads 3 times and then tails 3 times, that's your random number. As long as it's random, this is uncrackable. Then you get 111 0 0 0 and you exclusive OR with it. All right, so remember the exclusive OR. If they're the same, it makes it a 0. If they're different, it makes it a 1. So you're doing exclusive OR on these numbers. So it's bitwise exclusive OR. This is 0 because they're the same, 1 because they're different, and then both of these are the same, so it's going to be 0 0. And this now becomes, this is your ciphertext that you send across the internet or something, or through the mail. And anybody can listen in on it as long as they don't have the one-time pad. They can never get back the plain text. Isn't that crazy? Isn't that cool? This is symmetric key cryptography. So the ciphertext is going to be given to the receiver. They're going to get that. That's the 010100, the uncrackable thing, unless you have the one-time pad. On the other end, they also have the same one-time pad. They have the same key. They're going to do exclusive OR with that one more time, 111 0 0 0, and that will give them back the plain text. Because exclusive OR with the same thing twice just cancels itself out. All right, so they're different, makes a 1. They're the same, makes a 0. They're different, makes a 1. 1 1 0 0, and what do you know? That is the same as the original message, and secret stuff has been transmitted. Okay, so that's symmetric key cryptography. It's the easiest idea, I would say. As long as you can get together and agree on a secret key, then you're good to go. Sometimes, though, this is impossible, especially across the internet. People don't trust each other. There is a better way when you cannot get together and come up with the same key. You can use different keys, and that's where RSA comes into play. So RSA is a very popular, still very popular algorithm that is in encryption form, and it's named after the last names of the people who invented it. So these are the 3 people who came up with it. And we're going to use these boxes on the right to figure out how RSA works. It has to do with modular multiplicative inverses. It's a lot of weird stuff, a lot of weird math that we've learned about now. And it is so cool. It's going to work really well. So it is the backbone of the internet, first of all. Like you go to any website, like, I don't know, Canvas, for example. Connection is secure. Why? Why is it secure? Show me the certificate involved. It is using RSA under the hood, which is really fun to think about. So it's a type of public key cryptography, and everyone has a public key and a private key. And then some things you share with everyone, like the public key you share with everyone, and the private key you keep it only to yourself, all right? And you don't have to ever share. You don't have to do any key exchange. It doesn't have to be symmetric. It's fine. So this is the idea, okay? So the setup for RSA, or let me read these bullets in order, I guess. RSA is unbreakable because it has to do with large numbers that need to be factored. If you can factor numbers efficiently that are giant, then you could break RSA, but it's not computationally feasible to factor large numbers, right? That's the reason it's unbreakable. It has to do with math, some really cool math. And then here's the setup for RSA. So person A, Alice, is going to use, if Alice is trying to send a message to Bob, she's going to use Bob's public key. Bob shares his public key with the world, and she can encrypt her message for him using that key. And then Bob gets the message that was encrypted using his public key from Alice, and he's able to use his private key to decrypt it. And the encrypted form is not visible to anybody else. You need the private key to decrypt the thing that was encrypted using the public key. All right? So here's the setup. Here's Alice. Alice is the sender. If only I can spell Alice. And then here's Bob over here, the receiver. So in order for people to send messages to Bob, Bob needs to share his public key with the world. So anybody on the internet who wants to see it, he'll shout it out to them. Here's my public key. All right, so there's a concept of a public key and a private key. So Bob is sending that to anybody, including Alice, of course. And then Alice can use that. So she has her message that she intends to give to Bob. She can sign that with the public key. She can encrypt it with the public key and send that encrypted message using Bob's public key to Bob. And then Bob is secretly holding on to his private key. All right, and that magically will decrypt any message that was encrypted using his public key. All right, it's going to open that lock. All right, and so here's the setup to generate RSA keys, to encrypt and to decrypt. There's a lot going on. Let's walk through it together. So the way that you generate your public key and your private key is like this. You find two very large prime numbers. You call those P and Q. All right, so Bob's going to do this. Bob is generating his public key and his private key right now. All right, so it's all based on two large prime numbers, and it's very hard to figure out what they are at the end of all this. All right, so that's why it's secret, and everybody on the internet uses it still. So Bob computes a couple numbers. He computes n, which is p times q, those two numbers multiplied together, and then phi is equal to p minus 1 times q minus 1. All right, so those numbers multiplied in different ways. And then Bob is going to find any number, any integer, call it e, such that the GCD of e and phi is 1. So he's going to find a number that's relatively prime to phi, right? That's what that means, to be relatively prime. Here GCD with phi in that is 1. And then Bob will compute the multiplicative inverse of e mod phi. So all these numbers in different ways, they're working together. Bob will find the multiplicative inverse of e mod phi. That's that number that when you multiply it, we'll call it d, you multiply it by e, mod phi, you get back 1. It's the inverse, right? So it leads to 1 in mod phi land when you're working mod phi, and then those are your keys. Your public key is two numbers, actually. It's a pair of numbers, n and e. And then your private key is the D, okay? So that's that. And to encrypt something, what you do is you have your message. Your message is a number, of course. Everything in computers is a number. So you take your big, large binary number that is your message that you want to send to somebody. And for encryption, you use n and e. You take m to the power of e mod n, all right? So it's a big number, but you're going to modulus it down. And that computes your ciphertext. And then to decrypt using the private key, because they're multiplicative inverses, it works out. You can just take the ciphertext to the power of d, mod n still, and then you can compute the original message all over again. All right, so that's RSA. That's how you generate keys, and that's how you encrypt and decrypt. All right, so let's use these boxes, because this is what you're going to be using on your lab and in the homework. Let's do it all together. All right, so let's do just a baby form of RSA. So your public key, again, is two numbers. Secretly, it's a pair of numbers, n and e. And then the private key is just a single number. All right, so let's assume we start with p equal to 23 and q equal to 29. Those are our giant prime numbers for this example that we've chosen. Usually they'll be much, much larger. But let's figure out, let's do it in order. What are n and phi? All right, so n and phi. So n is equal to p times q, and phi is equal to p minus 1 times q minus 1. So all right, n is equal to pq, which is equal to 23 times 29. That's 667. And then phi, that's equal to 22, right, times 28. Multiply them after subtracting 1. So that's 616 for those numbers, all right? And then you're just going to pick a number, you're just going to keep trying them until you find a number that's relatively prime. So let's just pretend that we've tried a few random numbers and like 13 works out. Let's say that our e is going to be 13. Let's confirm, first of all. Let's confirm that it's relatively prime to phi, because that's necessary. E needs to be relatively prime to phi, so we'll do our GCD, confirm that. And then we also want to find d, the multiplicative inverse of e mod phi. So we can get these both in one fell swoop, right? Because of this, we can use the extended Euclidean algorithm to find that multiplicative inverse, okay? Assuming they're relatively prime and the inverse is, and that the GCD is 1, all right? So let's do our work on the next slide. We're going to need some room for this part. So, okay. I'm going to do, I need to find a number that is relatively prime to phi. I've assumed it's 13. So let's do the GCD of phi and that 13. All right, so GCD of 616 and 13. Better be 1. And then we're going to do the extended Euclidean algorithm as well. So 616 and 13, I'm going to do the GCD of these two. So all right, remember the setup. Let's do the 616 mod 13. So that gives me 5. So now I'm going to do 13 mod 5. So this is just the normal GCD. So that's 3, 5 mod 3. Oops. What have I done? There we go. 5 mod 3. 2 left over. 3 mod 2. Cool, the answer is 1. So that's going to be your final answer, because 2 mod 1 is 0. And so 1 is the GCD of 616 and 13, and then we need to do our extended Euclidean algorithm, extended GCD, to find the multiplicative inverse of 616, of 13, mod 616. All right, so let's do that. Multiplicative inverse of e mod phi. So we're going to do the extended GCD, extended Euclidean algorithm. So what are our equations? So I start with the rightmost one. What is 1 involving 3 and 2? Well, 1 is equal to 3 minus 2, right? All right, what about this equation? 2 is equal to what involving 5 and 3? Well, it's just 5 minus 3. That works out. All right, what about 3 involving 13 and 5? 3 is equal to 13 minus, it's finally something times 5, right? 2 times 5. Got a factor finally. And then this one, 5 involving 616 and 13. So 5 is equal to 616 minus, and then we're going to have to start dividing. So what's 616 divided by 13? It's 47. So it goes in 47 times into 13. And then there's 5 left over. So those are our 4 equations. And then let's start filling them back in until we get something involving these numbers equal to 1. All right, so we'll start with this one. 1 is equal to 3 minus 2, but what is 2? It's this thing. 3 minus, well, that's 5 minus 3. All right, which is equal to, all right, how many 3s? We've got, it's 3 plus 3, right? So we got 2 3s. 2 times 3 minus a 5. So that's that one. And then, okay, what is 3, though? 3 is equal to this, so let's replace the 3. That's equal to 2 times, we've got 13 minus 2 times 5, and then still the minus 5 at the end there from this part. And then, all right, how many 13s and 5s now? So we've got, I think, 2 13s. And then how many 5s? We've got minus 4 5s, and then minus another 5, so minus 5 5s. So there's that. And then finally, let's propagate one more time. What is 5 but that? So 2 times 13 minus 5 times, I guess I'm not great at writing the number 5. 5 times, well, it's equal to that. So 616 minus 47 times 13, which is disgustingly large. Okay. Well, let's do the math on this. How many 13s? All right, so you got 2 from this one, and then you've got plus 5 times 47 13s. Oh gosh. 2 plus 5 times 47. 237 13s. 237 13s, disgusting. And then minus 5 616s. So that should be the answer. That should be our final equation, this and this. So that's involving the 13 and the 616, getting us to 1. You can always confirm that you did it right. What's 237 times 13 minus 5 times 616? Okay, that worked out. That is 1. And then what we're looking for, remember which was E, which was phi, right? This is phi. This is E, and we're looking for the multiplicative inverse of E mod phi. So we're going to do mod phi on all these bad boys on this equation. So mod phi, mod 616, makes any multiple of 616 go to 0. Yes, there's that. And so we get the equation under mod 616 land, the inverse of E, of 13, is 237. And that'll be our answer. All right? That'll be our answer. So D, our number D is equal to 237. That's the multiplicative inverse of E13 mod phi, or 616. You can always confirm that, right? Let's write it back here first. You can always confirm that. So what we did, first of all, so we did the GCD of E and phi together, and we found that D was equal to 237. And you can confirm that that is the inverse of E mod phi, because you can do 237 times E, which was 13, mod phi, or 616. And that really does give you 1. Those are inverses of each other. That's perfect. And then now we have every number, finally. We have our public key, which is our N and our E. That's this 667 and 13. And then we have our D, finally. That's 237. All right? So let's say that we are Alice. We're trying to encrypt our message. Our secret message for Bob is 515. That's our secret number. All right? So let's encrypt 515 to compute the ciphertext. So our ciphertext is equal to our message to the power of E mod N, because we got the public key. We can use the N and the E to encrypt the message. Anybody gets to see those. So ciphertext is equal to M to the E mod N. Okay? So that's 515 to the 13th power mod N, which is 667. So all this math is going to work out to make all this work for us. Okay, so 515 to the 13th power is that giant number. But then you take it, mod 667. That gives you a more bite-sized number. These numbers are still huge when you use real large primes, but you get the idea. Easier to transmit this number across the internet. 265. That's the encrypted form of our original message. That is our ciphertext. All right? And this, nobody can crack it. Nobody can figure out what it was unless you had that private key, or you could factor numbers very quickly, and nobody can do that. All right? That is not possible until quantum computers become a thing. So, all right, or P is equal to NP, if you've heard of that. So let's decrypt that ciphertext now. Let's say that we're Bob. We got this message. Let's decrypt it by taking the ciphertext to the power of D mod N. It'll all cancel everything out because they're inverses. We'll get our original message back, and that's what we want to read. That's the secret thing meant for our eyes only. Okay? CD mod N is what we want to compute, which is 265 to the dth power, which is 237. Then mod N, which is 667. All right, so let's compute that and confirm. It better be the same thing. 265. First of all, to the 237th power. That's a giant number. Yeah? And then you do mod on that. Mod 667. Somehow, magically, the magic of math, we get our 515 back. And that was our original message meant for our eyes only. Nobody else was able to listen in because we use some giant prime numbers, right? So, yeah. The bigger the numbers, the harder it is to crack it, and people like to use very large numbers these days. So, yeah, that is RSA in a nutshell. It's a very popular algorithm, a very popular encryption method that involves a public key and a private key. All right, it is it's a non-symmetric kind of cryptography. It doesn't assume that anybody can listen in, it assumes that everyone can listen in. You just, as long as you keep your private key hidden and you use large enough prime numbers, at the end of the day, you are going to get encryption that nobody can break. So that's really cool, and it powers the internet, and we had to learn a lot to figure it out and understand it. But that is finally the end of our number theory and encryption slides. Hopefully you found this as exciting as I do. And yeah, I think that's all that I have to say this time. So I'll see you next time.